Please listen carefully.
Hello and welcome to GasGasGas. This is the best podcast for the FRCA primary exam. Our goal is to fill your brain with all this highly useful information. You might be in the gym right now, commuting, or ironing your scrubs. Regardless, the revision is eventually going to end, but for now, expect facts, concepts, model answers, and the odd tangent. Make sure to check out GasGasGas.uk. There's show notes there's loads more detail. Make sure to like and subscribe. Anyway, buckle up, get ready for your mind to be bent into a new shape, and let's get on with the show. Hello everyone, this is James at GasGasGas. Today we are talking volatile anaesthetic agents. We're going to introduce these and cover up the important physicochemical concepts that govern how they behave in a patient. We're going to think about how they behave physically in the environment around us or in a Tupperware box, and also touch on the pharmacodynamics of volatiles overall. We're going to touch on critical temperature, saturated vapour pressure, boiling point, as well as blood gas partition and oil gas partition coefficients. Tapping in on the definition of MAC and how that relates to oil gas partition coefficients, and talking in a little bit more detail how the blood gas partition coefficient influences onset time. I'm going to take a moment to apologise for the kerfuffle with the opioids quiz. The sound engineer, well, for the third time they've been sacked, and actually I think they're just going to they're going to take up video editing instead. There was an issue with the post-recording mastering that made that background music really hecking loud, and then also it somehow misaligned itself. So tremendous headache, and it took ages to originally align it and alter all the amplitudes of the volumes, etc, etc. And I just think, headache, not going to bother with that again. So I hope you can accept my foibles, and we're going to get on and chat critical temperature. So what is critical temperature? It is the crossover point where a vapour takes on the true behaviour of a gas. Now, it is hard, at least for my brain, to think about this from the perspective of a vapour. So I press forward and think about why it's a gas, and then consider the contrary to be why it's a vapour. So if you've got a gas and it is above its critical temperature, so that's like oxygen, hydrogen, etc., anything above its critical temperature, which is particular to it as a molecule or atom, you can apply as much pressure as you like and it will not shift phase down to a liquid. If you were to take sevoflurane vapour, i.e. that stuff that's zooming around your anaesthetic circuit, and apply pressure to it, it would begin to shift back into a liquid phase. Above its critical temperature, no pressure will get you there. So anything below its critical temperature that is floating around is a vapour, whereas anything above is a gas. So when you're doing a gas anaesthetic, you have the opportunity to be deeply pedantic and say, no, in fact I'm doing a vapour anaesthetic, but I am co-administering air, which is a gas. You could also argue that you're administering nitrogen if you're using an oxygen-air mix, as well as the other molecules that are in sparser concentrations floating around in our atmosphere, and there'll be some carbon dioxide in there too. I think we need to conceptualise a bit of a mental model here, folks, before we press further. We need to talk saturated vapour pressure. Again, this is something that made my head hurt, and there is crossover with this concept and humidity. We're not hitting humidity today. So you've fished out your bottle of sevoflurane from the cupboard, and you've somehow managed to unscrew the top, and you have your Tupperware lunchbox that is, an airtight one, thankfully, and it's empty, there's no ham sandwich, and you tip a bit of sevoflurane into your Tupperware box, and you close it up. What happens in this box? So some of that sevoflurane liquid will shift into a vapour phase. As this liquid shifts into a vapour phase, the remaining liquid gets slightly cooler. Now, why is this happening? It is happening because all of your molecules of sevoflurane in that bottle all have slightly differing amounts of energy in them. Some are a bit more energetic and some are a bit more feckless and lacking energy. We have to imagine this energy is heat energy, i.e. vibrating, jazzed up molecules. Some more jazzy, some less jazzy. The jazzy ones are more likely to escape off of the surface of your sevoflurane liquid and become a vapour and start bouncing around gleefully in the gas space inside your Tupperware box. Now, given enough time, and noting that this is a somewhat fixed space, an equilibrium state will develop whereby quite a few molecules have pinged off the top of the sevoflurane liquid and are bouncing around in the gas, but some of those molecules are also hitting the gas liquid interface, or vapour liquid interface if we're being proper, and returning to a liquid state. And there's an equilibrium that will eventually hit between the amount of sevo escaping and the amount of sevo returning between these two states. When that equilibrium is reached, and at a particular temperature, you can say that you have reached the saturated vapor pressure of that particular system. Now, sevoflurane behaves differently to isoflurane and desflurane, etc., etc. They all have slightly different saturated vapor pressures, SVP, SVP being the equilibrium state between vapor and liquid in a system. Now, if you were to take a big lungful of this sevoflurane in your Tupperware box, you'll end up with quite a large dose. Why? Because the saturated vapor pressure of sevoflurane is 21 kilopascals at 20 degrees. So if we've heated our Tupperware to 20 degrees and then taken a lungful of that vapor once it's equilibrated, we will be getting, as you can imagine, a stonkingly large dose of sevoflurane. Not good for us at all. It'll end up being 21%, more or less, sevo. And we know that that sevoflurane vaporizer will only actually let us get up to 8%. Presumably, we can imagine that therefore over 8% is certainly an overdose. And if you were to try and do a whole appendix on 8%, you'd end up in a very, very vasodilated, poorly patient situation. It would not end well, far in excess of what you need. And this is why we need vaporizers, because we can then control the fraction of sevoflurane we're administering to a patient. So saturated vapor pressure is agent specific, temperature specific, and environmental pressure specific somewhat. And this pressure is important because if you raise the pressure of that system, noting that we are below the critical temperature of this molecule, you'll end up with less becoming a vapor because there's more pressure. It'll be worth reading up about the triple point of water and also about the difference between absolute and relative humidity. That will help you appreciate how water vapor behaves and by extension how these other volatile anesthetic vapors behave. As a tool to try and remember the SVP of sevoflurane, you can remember that it's the same as the partial pressure of atmospheric oxygen, 21. So just to summarize that, saturated vapor pressure is an equilibrium point that's molecule specific, temperature specific, pressure specific, takes time to achieve, and is the rate of liquid to vapor and vapor to liquid is even. Now, if you were to take off this vapor from this chamber through a tube, you would end up with more agent shifting from liquid state to vapor state. But we should note that we've pulled off the warmest molecules at this point in time. So now your system has dropped in temperature slightly. So you will end up with a lower fraction of molecule equalizing to that new vapor state until the system warms through again. So if you're pulling off rapid amounts of gas from your chamber, the chamber cools, the amount of volatile you're extracting goes down, and then you have an unclear concentration that you're delivering to your theoretical patient. This is why vaporizers are important. There are contraptions in there that try and facilitate constant temperature, as well as mechanisms that modulate the amount of volatile pulled from the chamber in order to compensate for temperature changes. We'll talk vaporizers in another episode far into the future, I'm sure. You also need to learn about boiling points of volatile anesthetic agents. All the volatile anesthetic agents have different properties and different boiling points. Why are we really interested in boiling point? Well, the easiest way to illustrate this is to compare our dear bottle of yellow sevoflurane with our bottle of blue desflurane. Sevoflurane boils at 59 degrees. Now, I can totally agree that most NHS hospitals probably don't get to 59 degrees. Although I'm sure in that heat wave, when the air conditioning fails and you've rolled up your scrubs into shorts, much to the horror of everyone in the room, it's not quite 59 degrees. So the sevoflurane is not boiling. But desflurane, interestingly, boils at 23 degrees. So if you're in a moderately warm room, or perhaps on a lovely beach in Greece somewhere, and you spill some desflurane on the floor, it rapidly will shift into a vapour. It'll evaporate. That puddle will disappear. Unfortunately, that puddle will disappear into a small cloud of very, very concentrated desflurane before it gets blown away. If this were to occur inside our Tupperware box, we would end up with a very large amount of desflurane vapour. This leads to a moderately tricky situation whereby we may inconsistently deliver differing concentrations of desflurane if we were to use a standard bit of vaporizing apparatus. And that's why you've got to plug in your desflurane vaporizer. So it's bad for the environment because desflurane hangs around for ages, and it's bad for the environment because it takes electricity to actually use the damn stuff. If you don't use electricity and you don't intentionally warm desflurane above its boiling point of 23 degrees, you won't know how much desflurane you're giving to your patient. Desflurane vaporizers work in a different manner to inject a certain amount of very concentrated desflurane vapor into the system in order to avoid this lethal problem. Now, what about blood gas solubility? Now we've spoken a few about the physical properties of volatile anesthetic agents. This is a physical property of it getting in and around a human. So what is blood gas solubility? Well, the first fact to note is the lower your blood gas coefficient, the faster your drug onsets and offsets. The less soluble, i.e. the lower the number, the less able the volatile anesthetic agent is going to be able to sit inside blood. So you're probably thinking, and this is exactly where my brain went as well, how the hell does it go quicker then if it doesn't even want to be in the blood? That doesn't make any sense. And this is because it really bears down on the pressure gradients or the concentration gradients you're exerting on the human with the sevoflurane. If you fill their alveolus with sevoflurane, it only has one place to go. So it'll sort of, I don't want to, but I'm going to have to get into the blood. And it gets into the blood. Except for now that blood has been ejected around the body via the left ventricle and it's in the brain. And the sevoflurane is like, oh, well, I hate blood, but brain, that looks slightly more attractive. So it hops out of the blood into tissues. Obviously, the more perfused the tissue is, the more sevoflurane is initially delivered to it. So sevoflurane has a blood gas partition coefficient of 0.65, whereas desflurane is at 0.45. So in an exam, you would say that desflurane theoretically has a faster onset time and offset time, which is proven in practice. And you could note that isoflurane, with its blood gas partition coefficient of 1.4, takes longer to onset and offset, noting that offset occurs in much of the opposite direction. When you reduce that alveolar volatile anesthetic agent fraction, you shift the concentration gradients from lots in the lung to some in the brain and not very much in the lung, and it will start creeping back out. It would certainly be worth listening to that compartmentalized volatiles episode early on in this podcast that goes into this in slightly maniacal detail if you want to really get to grips with this. What about oil gas solubility? So oil gas solubility dictates the potency of the agent. So it's nothing to do with onset. It's all about potency of agent. And this does conveniently and expectedly marry up relatively well to the MAC values of these agents. More numbers you've got to remember, folks. So by that virtue, you can sort of work backwards and forwards a bit with MAC values to try and figure out your question about which is more soluble or less soluble, or which has the higher or lower MAC between these drugs, the joyful SPAs that you get to excitedly do. So isoflurane, MAC of isoflurane 1.2, sevoflurane, we'll call it 2, some places say 1.8, and desflurane requires an end-tidal fraction of around 6%, 6, to achieve a MAC. So we can now think backwards from that. Well, desflurane, 6% end-tidal, that's, you gotta get a patient's brain to like 6% desflurane for them to have a MAC of 1. So you'd expect that it is quite oil gas insoluble, i.e. it is less potent, so you need more of it. So these are the inverse of one another. Low oil gas solubility, generally higher MAC. High oil gas solubility generally will net you a lower MAC target for the drug. So desflurane's oil gas solubility is quoted as 26. Sevoflurane 47 to 54. Isoflurane 91. Now if you check out one of the references in the show notes, takes you to BJA article talking about all these things, and you can see their lovely tables that they prepared in order to perhaps get to grips with this in even more detail. So now we know about potency of volatile anesthetic agents, the onset-offset time of volatile anesthetic agents. But it's probably worth just mentioning this thing called wash-in rate. And there's lots you can do to alter wash-in rate. Again, we've spoken about this in a previous episode. But the important thing to consider is that a drug that is quite soluble in the blood and therefore takes a long time to work, you may end up fighting to achieve a high enough concentration before your propofol wears off. This is much less of an issue with drugs of today, but if you were to induce someone with propofol and then try and get them deep on ether, you'd be waiting a really long time, and you most certainly would end up with awareness in the middle, because it's just so hecking time consuming to get them deep enough with ether or chloroform. That's why we have more modern agents. There are excellent graphs, I think they're on e-learning for health, that try and describe these wash-in rates. This can either just be Mach on the y-axis and time on the x-axis, or sometimes describing the time it takes for the fraction of inspired volatile agent to marry up somewhat more closely with the alveolar fraction, which is a surrogated by the end tidal volatile agent fraction or percentage that you see on your anaesthetic machine. Now, I think the fraction inspired over fraction alveolar graphs are in Peck and Hill, I think. Again, a book that you should definitely open earlier rather than later in your primary FRCA studying. I still regret waiting until the week before the exams to open this book and realise that actually everything was there. So just open it, even though it's intimidating, open it. Now, these wash-in curves probably follow exponential functions, or whatever you call them, exponential or logarithmic, as opposed to linear processes, because remember, you're reaching a state of equilibration, and the closer you get to equilibrium, the slower you go to get there. So you can end up with a steep bit of a curve and then a shallow bit of a curve that takes you a while to reach equilibrium. Although I suppose technically you never really, truly ever really get to the end. Who knows? So just to perhaps labour the point of awareness, we've induced an anaesthetic in the anaesthetic room. We've done a few bits and pieces, and we've now transferred into theatre. In the anaesthetic room, we might have done a nerve block whilst the patient's asleep. Maybe we did it awake, but probably asleep. And we've transferred them into theatre, and now we're doing WHO safety checks. We've messed around, positioning them more, and there's been quite a lot of time between delivering that volatile anaesthetic agent and the surgeon actually picking up the diathermy or the scalpel. So this sort of programmed delay is actually very convenient for ensuring that you achieve an adequate depth of anaesthesia before surgical stimulus. However, we do find ourselves in situations where that time is very much shortened. For example, you're anaesthetising someone in theatre because they're a bit poorlier, or you're doing an emergency obstetric general anaesthetic for abruption, fetal bradycardia, awfulness, in which case your time to wash in volatile agent is significantly shorter. You may get away with being covered by that initial propofol dose and the surgeon jumping up and down wanting to get started. They start whilst actually it's the propofol that's keeping them asleep and not the volatile. But if they've got an exceedingly high cardiac output and they're equilibrating that propofol away from their brain quite quickly, you might end up with awareness. So you should certainly be aware that you should overpressure them with volatile in that situation, and or give extra doses of propofol to maintain depth of anaesthesia. And be aware that that little jolly transfer from the anaesthetic room where there's very little stimulus and the propofol's soaked in and not much is going on, the threshold for awareness is still present, but it's they're less stimulated, they're less likely to be aware than if someone is trying to jump into their abdomen to rescue a poorly baby from a situation. The one saving grace in obstetric situations is, for some inexplicable reason, they do seem to require less volatile anaesthetic agent to achieve 1 Mach. But we know that obstetric anaesthesia has a higher rate of accidental awareness under general anaesthesia, so clearly it happens. So just be super thoughtful about that if you end up in that situation, although thankfully rare to require a GA for a section. But that takes us nicely to thinking about things that influence Mach. This always comes up in exams, so it's certainly worth digging out a table that compares clinical states that require more volatile anaesthetic agent or less volatile anaesthetic agent. You could imagine that if someone has had a load of heroin suddenly, then they'll probably need less sevoflurane to be anaesthetised than someone who has in fact been a heroin user for yonks but hasn't had any in 24 hours. They're probably going to be rattling. This also bears true for hypothyroidism and hyperthyroidism. I'm sure you can work out which way round those are. And interestingly, low sodium and high sodium. Low sodium, dosier, less volatile. High sodium, need a bit more. It's equal for hypo and hyperpyrexial or thermic states, and a number of other states, which you will find when you dig out that table. But you can generally work it out as to states that make your central nervous system more jazzed up or less jazzed up. But I've brought up Mach and I've not actually told you what it is. Now, hopefully, if I were to pause for a second, you could actually tell me what Mach is. I'm sure you should know it by now. If not, you didn't listen to that previous podcast episode yet. So you're going to say it now. Go on. The definition of 1 Mach is the volatile agent fraction end tidal in a patient, that means that they will not move when they receive a standard surgical stimulus, skin incision, 50% of the time, i.e. 50% of the subjects wriggled, 50% did not wriggle. Caveats to this are there were no other opiates on board, no other analgesic agents, and no other anaesthetic agents. So this is a pure sevoflurane maintained depth of anaesthesia. The standard incision is a phalangeal incision. This is the one that's used for caesarean sections classically. Now, they've used this as a surrogate for will the patient wriggle or not. It doesn't tie directly to awareness, because actually the incidence of 50% awareness versus 50% not awareness is actually at a lower MAC, but a MAC of 1 is generally a safe place to be, where you are unlikely to end up with awareness because you've got a nice margin of error before getting down to MAC fractions where you're more likely to be aware. Check out the episode on MAC earlier in the podcast series to really try and get a better feel for what the cutoffs for awareness are, but also the cutoffs where you will see a completely obtunded sympathetic response to surgery, amongst other things. Because you've got MAC asleep, MAC aware, MAC bar, it's all there. And you might have spotted this wriggliness is much more prevalent when you're doing a Tiva anaesthetic with propofol than it is with a volatile anaesthetic. And that's because volatiles damp down your spinal cord quite a bit more than propofol does, and also has a fairly significant effect on causing neuromuscular blockade / relaxation, quite synergistic with your neuromuscular blocking drugs as well as your magnesium and gentamicin that make you floppier. You'll probably see that wriggliness a lot more if you're being a bit weird and doing a propofol TCI and giving fentanyl boluses. This is because remifentanil is a very, very potent analgesic and very much does make people quite still. Whereas if you're kind of gone a bit weird and you're using large amounts of fentanyl and then propofol TCI, you do see wriggliness more. So what about the more detailed pharmacodynamics? Because we've just talked about wriggly patients, but that's not very clinical. If you start telling an examiner that patients are more or less wriggly, you ain't using scientific terminology and you're not doing yourself a favour. So we need to think about the pharmacodynamics of volatile anaesthetics in a bit more detail. How do they work? Well, there are two schools of thought. One of them is now in the bin. That is the historical theory called the Mayer-Overton hypothesis. This tried to correlate the fat solubility of an agent with its potency, basing it on the concept that if there's more fat solubility, then it's going to soak into more lipid bilayers of neurons and block their function and cause loads of mischief. This kind of fell flat on its face once we started getting some quite fat insoluble anesthetic agents that caused anesthesia. Kind of stuffs that in the bag, doesn't it? So we started thinking about the protein-based concept of mechanism of action. Proteins being our beloved friends, the GABA A receptor and NMDA receptors, and also another presumed target of volatile anesthetics is the 2-pore potassium channel. If asked in an exam how do volatile anesthetics work, you could probably open with they allosterically modulate GABA A receptors and may also have NMDA and potassium channel activity, altering synaptic transmission of neurons within the central nervous system. Because we know that these agents bind to these things and we know that those things do stuff. Now, how does an anesthetic agent actually render you without consciousness? That is a question for the neuroscientists. If you want lots of detail on this, check out Miller's Anesthesia. I think page 488, depending on your edition and beyond, will elaborate in a delight of detail on volatile anesthetic agent mechanisms. But no one really knows. I've had a patient who was a pharmacist ask me, how do anesthetic agents work? And, I had to look at them in the face and say, oh, well, yes, axon receptors in your brain, a GABA receptor, which alters how those neurons work, but actually how it renders you unable to form memories and asleep is something that is not well understood. They looked a little bit aghast. I think perhaps had decided that they wish they hadn't asked the question because, they were sort of discovered in a bit of a black box-ish manner. Here, have a whiff of this. Oh, look, you're unconscious. Well, that's a useful thing. Maybe we could make use of you being unconscious so we can chop your leg off without it being quite so excruciating. And, even in this day and age, we are in a situation where we know it works. We're not quite sure exactly how it works, but we know it works. Fascinating, really. Now, I would argue that telling a patient that we don't know how something works is not exactly an effective communication strategy. Equally, it is not a lie. So we talked about mechanism, and now we should probably outline some of the side effects of volatile anesthetic agents. Now, each agent actually does have a particular subset of side effects that are relevant to it. I'm just going to cover the broad stuff here. So cardiovascular effects, because remember, we should always break these down by organ system. Broadly speaking, volatile anesthetic agents drop your blood pressure, and in higher doses, they can also cause bradycardia. From a respiratory perspective, there is often a dose-dependent reduction in respiratory rate. This can be somewhat utilised, and historically was, in that if a patient got too deep breathing their chloroform, ether, whatever, they'd breathe less and they would wake up a bit because they'd breathe less and they'd metabolise a bit more. Now, that might help in a sort of marginal realm of that spectrum of asleepness. But if you're giving 8% sevoflurane constantly, the patient might stop breathing, but then they're full of 8% sevoflurane and none of it's coming out again. So I don't really think that's a perfect way to administer an anaesthetic. Most of them cause bronchodilation, though, which is useful. From a CNS perspective, obviously, they hypnotize you, but also can cause a degree of neuromuscular blockade and smooth muscle relaxation. Much like you get the bronchodilation, you can get uterine atony, which is something of concern in your GA section, where you end up with a higher instance of obstetric hemorrhage. All volatile anesthetic agents can also trigger malignant hyperpyrexia, which is an emergency. It is very rare, and it's something we will cover at the end of this volatile anesthetic agents chapter with an episode on MH. All of these things might come up in the exam, but one of the favoured questions, or historically favoured questions, is what are the characteristics of an ideal agent, blah blah blah. You could apply that to a hypnotic agent, a pain relieving agent, etc. But what about the characteristics of an ideal volatile anesthetic agent? So you probably should break this down into useful pharmacological properties and useful physical properties. Pharmacological properties, think about, the patient experience and side effect profile you want. You would be masterful to break that side effect profile down by organ system. You would want it to be cardiovascularly stable from a respiratory perspective, pleasant for the patient to smell, non-irritant, and would not cause respiratory depression, but again would be conveniently bronchodilating. You'd want it to be stable from a metabolic perspective, not mess with any gluconeogenesis or steroidogenesis, and to not be metabolized into toxic metabolites. It would be very useful if it had analgesic properties, i.e. some useful NMDA receptor modulation, and you would not want it to increase intracranial pressure or reduce your seizure threshold. From a physical properties perspective, ideally you would want it to be non-toxic to patient and staff, non-flammable and certainly not able to explode. You'd want it to be stable in light so you didn't have to squirrel it away in a corner in the dark, and stable at room temperature with a boiling point that means that it had a predictable saturated vapor pressure. Ideally, that saturated vapor pressure would be quite high, so it would vaporize simplistically and easily in your vaporizing device. You would want it to rapidly break down in the environment and have minimal to no global warming potential, and that it also would have no propensity to soak into your tubing, be that plastic or rubber, i.e. halothane. From a kinetics properties perspective, you would want it to have a low blood gas partition coefficient, so it had a rapid onset and offset, and have a high oil gas partition coefficient, so it was more potent, requiring less agent to achieve depth of anesthesia, meaning you could use it less. And last but not least, you would want it to be cheap, because you don't want to be spending loads of money. And that's an excellent way to approach that sort of question. Break it down into sort of physical properties and patient-relevant properties with side effects. Never forget about how you administer it and how expensive it is. So what did we cover there? We've covered blood gas partition coefficient, oil gas partition coefficient, why boiling point is important, what saturated vapor pressure is, and I've sort of flagged you off to, you need to go read about humidity, and that will help cement that. Touched on reasons why you might need more or less volatile anesthetic agent. Thought about wash-in curves and the concept that it takes a while to achieve depth of anesthesia with volatile, because you've got to breathe it in, it's not just injected in someone's veins. And closed up with the ideal approach to an ideal anesthetic agent question. So what are we going to cover in the next episode? So we're certainly going to do episodes specific to each volatile anesthetic agent: isoflurane, sevoflurane, desflurane, halothane. We will do a combined nitrous and oxygen episode There is a Viva cast on this, but I'll just tie it all together properly. Definitely dab in with an episode on the history of volatile anaesthetic agents. We'll look at ether, chloroform, halothane, and maybe their first use, because that'll be a bit of a laugh. Definitely, we will do a quiz at the end of this, but we will also, before then, have episodes on malignant hyperpyrexia, thinking about its mechanisms of treatment. And then maybe just for fun at the end, we'll do xenon, because that is also a general anaesthetic-inducing noble gas, which is quite mad, really. Anyway, thank you very much for listening. If you really enjoyed this episode, feel free to fire up a donation. It'll help keep the show running, cover the costs of the website, cover the costs of hosting. It would be much appreciated. Thanks for listening, guys. I hope you found it useful, but if you found it awful, do let me know. Please like and subscribe, register with whichever podcast platform you find yourself using, and leave a comment if you think I need to square something away. I just want to make sure that you guys know that every day you are getting better at this. There is a bucket of content to try and consume, and it is like drinking from a fire hose. Take it day by day, don't overcook yourself, don't freak out, and keep studying.